Hello everyone, I'm Weiquan Fan from South China University of Technology. The topic of my speech today is Adaptive Domain-Aware Representation Learning for Speech-Emotion Recognition. This is my contents. Let's see the introduction. First, what's emotion? Emotions are biological states associated with the nervous system brought on by neurophysiological changes variously associated with thoughts, feelings, behavioral response, and a degree of pleasure or displeasure. Psychologists have used methods to map emotion-related response onto a more limited number of dimensions, such as valence and arousal. Valence is how positive or negative the experience feels. Arousal is how energized or elevated the experience feels. Speech emotion recognition using speech to recognize human emotions is a crucial part in human-computer interaction. So, what's the challenge in SER? Representation learning is challenging due to much variability from speech emotion signals across diverse domains, such as gender, age, language, and social cultural context. Let us take the gender as an example. It has two domains, male and female, green and yellow. Some researchers map data of the two domains to a common shadow domain to find domain invariant features. But it is limited due to the lack of domain knowledge. Some researchers train a model for each domain separately, and some find domains which are orthogonal to the common domain based on A, and map data to domain invariant and domain-specific feature according to the given domain knowledge. However, it needs to know the domain in advance, and it cannot deal with the unknown unseen domain. So, we propose our method, which can automatically select domain A or domain B according to the learned domain knowledge. Our adaptive domain-aware representation learning adopts the multitask learning framework, consisting of domain classification and emotion recognition. The domain classification task identifies the domain and generating domain-aware knowledge. The emotion recognition task predicts emotion using domain-aware knowledge. Let us see the detail. In the domain-aware attention loyal, time pooling and channel pooling are used to highlight the frequency information. The information is transformed to the domain knowledge using 2FC. For domain-aware attention embedding, the knowledge is diagonalized and multiplied by the feature maps. Then we can get the new feature maps with domain knowledge, and we can use it to predict emotion. Considering the temporal uncertainty of speech, we use multi-scale CNN to extract high-level features, whose basic unit is multi-scale convolution here. Specifically, firstly, Convolutional kernel with different scale are applied to convert the input 3 times 3 and 5 times 5. Secondly, the future maps after convolution are concatenated along the channel dimension. And finally, an average pooling lawyer is used for downsampling. Here is the loss function. For the domain pathway, only the most basic cross-entropy loss function is used. For the emotion pathway, cross-entropy loss and center loss are used. Here, center loss is to cluster the futures, since the emotional expression is very diverse. So the final loss function can be described as this formula. Here we set gamma 1 equals gamma 2 equals 1 to maintain the balance of the two pathways, and gamma 3 equals 0.5. Here is the specifications of our ADARL. We can see the parameters here. Now let's see the experiment. In our experiments, we use the IEMOCAP datasets. It records approximately 12 hours of audio-visual dialogue data for 10 actors, which are divided into 5 sections with 2 speakers each. The label we used includes neutral, happy, sad, and angry. Let's see the feature extraction. For data augmentation, we divide the sentence longer than 3 seconds into multiple non-overlapping subsegments with 3 seconds and discard the rest. For each subsegment, STFT with humming window length of 20 or 40 milliseconds and a window shift of 10 milliseconds is performed, followed by a log operation and z-score normalization. So for the frequency axis, only the 0 to 4,000 Hz band with significant information is reserved. For the time axis, zero padding is applied to get 300 points. Therefore, a 3 times 400 times 300 spectrogram is drawn for each subsegment. Here is the ablation studies. From this figure, we can observe that the backbone network has achieved acceptable performance. The domain invariant model with adversarial multitask training has improved to a certain extent. And with the domain-aware attention, the performance of the model is further improved. This is because the domain-aware attention solves the interference problem caused by the domain diversity through adaptive embedding domain knowledge to the emotion feature space. Let's see the confusion matrix. We can find that the samples of angry, sad, and neutral achieve good performance, especially for sad samples. Only few samples are mispredicted. Intuitively, Set samples have obvious voice characteristics such as low pitch and slow speed. After the domain-aware attention, our performance has been significantly improved, especially for happy. However, there are still some happy samples were mispredicted as neutral. We speculate that the reason is that many people don't react too much in voice when they are happy, but instead respond to facial features such as smiles. So in our future, we will try multimodal fusion. Here is the future distribution. We can observe 3 obvious clusters of angry, neutral, and sad. Note that the samples of female and male are clustered in similar position for each category with ADAR error. We compute the L2 distance between genders, female and male, for each category sentence. It can be found that each distance between male and female is reduced with domain-aware attention, which means the problem of domain diversity has been improved. Here is the results. The result in both WA and UA, weight accuracy and unweighted accuracy, are better than the others, which demonstrates that the proposed framework has outstanding performance and good generalization. Finally, future works. In our future works, we will try multimodal fusion and make full use of the complementarity between different modalities, includes audio, video, and text. We believe it can improve to a certain extent. And also, we plan to build a large database and publish a pre-trained model for emotion recognition. That's all. Thanks.